All right, so along with our definition of a derivative comes a lot of our familiar rules, like the derivative of a constant times a function is a constant times the derivative. Derivative of a sum is the sum of the derivatives. We have the product rule for derivatives, and then we also have the quotient rule for derivatives, and that's the one we're going to prove now. So quotient rule says that the derivative of a quotient is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. And though I won't often write it down, this of course implies or is under the assumption that g of c is not zero, right? We're not dividing by zero. All right, now the only tool we really have is to work with the definition of the derivative. And so that's our difference quotient. We take the limit as x approaches c of the function, which in this case is f of x over g of x, minus the function evaluated at the point, f of c over g of c, and then divided by x minus c. And from here, it's algebra and seeing what falls out. So I'm going to get a common denominator in the numerator here, which will give me f of x g of c minus f of c g of x all over g of x, g of c, and x minus c. All right, well that doesn't reveal anything immediately. So what we're going to do is use, again, one of our favorite algebra tricks. In the numerator, we're going to add a clever form of 0. Right? So we're often either multiplying a clever form of 1, multiplying by a clever form of 1, or adding a clever form of 0. And so this is going to become f of x g of c minus f of c g of c plus f of c g of c minus f of c g of x all over g of x, g of c, x minus c. So the quantity that I've added and subtracted is the f of c, g of c. Right? So I've done nothing to change the value of the expression. That is just adding 0 in the numerator. But if we take a look ahead, that's going to be useful because this g of c can factor out of the first two, leaving me with an f of x minus f of c. And then when I divide by that x minus c, I'm going to end up with the derivative of f. And I know that that should appear. And similarly, from the last two terms, I can pull out an f of c, or I guess technically here a minus f of c, and I'll be left with g of x minus g of c. And that suggests the derivative of g is going to appear. So let's take a look. We're going to have limit as x goes to c, x minus f of c, g of c, over g of x, g of c, x minus c, and then I've got minus f of c, g of x, minus g of c, g of x, g of c, x minus c. All right, so the limit goes with all of this. Now it's really tempting to cancel this g of c here, but actually we don't want to do that this time. We want that g of c squared to appear in the denominator, and if we cancel it now, we'll just have to put it back later, finding a common denominator. So leave the g of c, and now we're just going to go ahead and take all the limits. So this piece here is my f prime of c. And now I've got g of c. And this piece here is g prime of c. and they have the same denominator, and that denominator will be the limit of g of x as x approaches c times g of c. And that gets me my g of c squared. Right. Now, I've actually kind of skipped over a couple of things. One is that I'm using the algebraic limit theorem, right? The limit of the difference is the difference of the limits, and I'm using the products and quotients as well. But I think it's okay to just go straight to the limit. The second thing, which we do need to mention, is I said that the limit of g of x is equal to g of c, and so that g of c squared appeared. And that's actually because of the theorem we proved in the last video, right? So we already showed that if a function is differentiable, then it's necessarily continuous. So the fact that we assume g is differentiable means that g is continuous, and that means that the limit of g of x as x approaches c really is g of c. Right? So that's not a step that I wrote down explicitly, but we are using a theorem there to get this final result. So here's our quotient rule. That should be the end. So you'll be asked to do a couple of these sorts of proofs in the problem set.